Okay, so what this class is about. So we're going to be teaching modern numerical techniques for a wide range of PDEs. And by PDE, we mean partial differential equations. We are going to learn a lot of similar things in this class. And this is going to be useful in many science and engineering applications. So, like a lot of modern engineering and science relies on numerical methods, relies on scientific computation or engineering computation. And this is, solving partial differential equations is a big fraction of what computational simulation is about. So for example, a lot of us has benefited from weather forecast. And weather forecast is one of the examples of numerical solution of partial differential equations. In the context of this class, it is an initial value problem. The evolution of the atmosphere, like the temperature, pressure, moisture content, is modeled as a partial differential equation. And the current state of the atmosphere is measured. That is set as an initial condition for the partial differential equation. And we solve this partial differential equation forward in time to, let's say, several days later. And the status of atmosphere at that time is our weather forecast. All right, so this is one of the examples in science that solution of partial differential equations using numerical methods has benefited us a lot. Another example is that the design of this very building we are sitting in may be a result of solution of partial differential equations. Because the building codes, like where you should put smoke detectors, where you should put like automatic sprinklers, is really designed around possible scenarios of fire. And in order for people to, when you build a building, in order for people to decide is the placement of sprinklers and smoke detectors and things like that, is that appropriate? We solve partial differential equations to model the evolution of fire and the resulting propagation of smoke and the temperature. And this is used to determine what is the building code that should be enforced when somebody remodel a room or build a new building. So that's another example that numerical solution of PDEs are used in practical everyday life. And my favorite example, let me dim the light a little bit. Okay, that's good. My favorite example is in aerospace engineering. So the solution of partial differential equations that governs fluid flows, for example, on the space shuttle on the left and around the helicopter on the right. These are used to really guide engineering designs. So before we have a space shuttle to launch or to test, like how do we design the aerodynamic shape of the space shuttle? These are all designed based on numerical simulations. And we know like aerospace engineering, doing experiments or doing flight tests is really expensive, costs a lot, takes a long time. It takes a long time to build like a space shuttle test article and actually to fly it. And it is potentially very dangerous. So having numerical simulation to replace this both saves time, saves money, and potentially saves lives. So if we can build numerical simulations that we can really trust, this is really a great benefit to the advance of aerospace engineering and science. So these are application of numerical PDEs in aerospace engineering. Let me try to damp the wiggles. I don't know why these are. Anyway, so let's see if is that fine? Like, does that bother you? No? Okay, that's fine. Okay. Good. So now the question I want to ask you is, what do you want to learn in this class? Anybody? Okay, I'm going to start ask from the very back. Could you please say what do you expect to learn in this class?
I'm interested in finite element models.
Finite element models. Okay, great. What do you expect to learn?
Besides finite element, I would like to know more another techniques to solve the partial differential equations.
What equations?
This PDF equation.
Okay.
There are several techniques more than finite element method.
I see.
And I would like to have a view of all of these numerical methods.
So you want a broad
Yeah.
knowledge of methods to solve PDEs. Okay, how about you?
I'm interested in volume integral equations.
Volume integral equations. Volume integral equations. Okay, very good. And what do you want to learn?
I already studied finite differences, so I want to see other methods to solve the problems in better ways.
What problems?
So usually it's not engineering numerical simulations. So it's the same thing about propagation of something, but it's not heat or electricity, which is most of the applications, but different kind of propagation. Sometimes you can have any kind of spread in a network. But the problem
Spread
is,
in a network.
But the problem is most of the examples in these courses usually take real life examples of discretization of a physical system, and so you get a very clean network. But usually I deal with networks that are not as clean as the ones we use.
Cool, you want to use PDEs to solve network problems. Anybody else has a different from the people who already contributed? What do you want to learn that is different? Yes?
Solving Navier-Stokes equation.
So we have Stokes equations. Okay, that is very specific. That's great. And I also like solving Navier-Stokes equations. Anybody else? Yes.
Also, the applicability of certain methods, certain types of PDEs, and the limitations why you cannot use one method for certain PDEs versus others.
Good. We want to learn what is the applicability of different methods to different problems and what are the limitations of different methods. So that when you have a problem, you know how to choose which method you want to apply. That's very good. We are going to teach that. And what else? Yes?
What do we do when we have nonlinearities?
Nonlinear equations. Okay, great. We're also going to teach that. So how to solve nonlinear equations.
I want to learn how to develop a CFD code.
How to develop code
Yeah.
for solving differential equations. That's also very important. That's one of the primary focus of this course. You are going to find just in this course at MIT that is a little bit different from other PD classes is that we have more focus on helping you to gain skills in developing solvers. What else? Okay, I think we are very good. I think I have a understanding of what you want to learn, and if you think of something else, just email me. I think it'll be great to have for me to have a knowledge of what you want to learn. All right. So what we are going to cover is basically in sequence 4 different methods of solving differential equations numerically. They are finite difference, finite volume, finite element, and boundary element methods. So boundary element methods are also known as integral methods. So that's just another name for it. Another thing we are going to learn sometime early in the process is direct and iterative solver methods for equations that is a result of the discretization methods. So we have a PDE, we discretize into something that is non-differential. It is either an ordinary differential equation or even simpler than ordinary differential equation, an algebraic equation. We are going to learn how to use methods to solve this kind of large system of equations as a result of partial differential equations. That is in some sense unique to PDEs because for for other applications, it is kind of rare to get a system of equations as large as you have in solving a PDE. So there are some particular direct and iterative solution methods developed for solving discretized partial differential equations.